Thank you, Bernhard, for the nice introduction. I guess you can hear me. Is that correct?
Yes. Yes.
Okay, very good. Welcome to this short section on acoustic self-awareness of autonomous systems, where I actually would like to promote the use of the acoustic modality for self-awareness in autonomous systems a bit more. Next slide, please. So what you see on this slide, a very simplified version of autonomous systems in gray, where I highlighted the perception and the cognition part each. And I embed this now into a physical environment where we have a desired source, we have background noise, interferers, we have even feedback from loudspeaker signals, but we also have ego noise, and this is the part which you would probably see as most interesting for autonomous systems, and we will come to this later. So the question is really how to, please stay with the previous slide. The question is really how to exploit the acoustic information that you can gain from the environment and from yourself for supporting your self-awareness of the autonomous system. And now next slide, please. So I have one slide for perception and cognition each, and then it's all for today. So essentially, perception has to analyze the world of sounds, and that involves a lot of classical acoustic signal processing challenges, which are used in many other domains. And it includes source localization and tracking, which is the basis of SLAM, so where the M stands for the mapping in the end. We also have to solve source separation problems and suppression of interference and noise, and acoustic feedback control. These are all classical signal processing challenges which are commonly addressed now if you have multiple microphones by multi-channel signal processing algorithms in the time frequency domain. And they are very early on mostly model-based, but now they are increasingly data-driven, and that it hints to machine learning as a buzzword. But what is specific for autonomous system is obviously the ego noise, which you can model and learn from the microphone signals. And you can actually generate a noise which is then giving you a lot of information about the environment, like using the steps of a moving robot, of a humanoid robot moving in a room, and you just record the data. You can also use, of course, a lot of reference information from other modalities. I mentioned motor data here, and you can also use video data for localization, obviously. That's all in the back, but we state here that the most important thing on the acoustic level is the ego noise, which is specific for our autonomous systems relative to the previous. To other application domains. And with this, may I have the next slide, please? I move over to cognition. On the acoustic level, it essentially means that you have to understand this world of sounds where you are in. And obviously, this highly depends on the scene you're in. And you may think of a humanoid robot which has to conduct speech dialogues interfacing with humans, and it can be multiple humans at the same time, and this is an established field of research in other domains, but not so much for robots yet, especially if you look at cocktail party scenarios. If you think of an autonomous car as another instance of an autonomous system, you need to understand the sounds of street life. And of course, factory environments are a little less complex. And I don't want to expand on military, that's not my area, but those who are knowledgeable about it know about the diversity of sound scenes that you can face there. In the end, it all boils down to sound classification and the understanding of the respective scene and the languages which are used to describe these scenes. And that leads us directly to this broad and ill-defined term of artificial intelligence, which is essentially exploiting data that you can gather from the environment, and then you apply all these algorithms to extract meaning from it. And Carlo gave a nice set of techniques already for that. Specific for autonomous systems here is obviously that these algorithms have to deal with real-time constraints. They have to adapt quickly to changing scenarios. The acoustic scenarios can change very quickly for autonomous systems, and very often the autonomous systems are obviously resource constrained, so you may not always be able to reach out to a cloud and to do the computing for you. And with this, I would like to hand over, not forgetting, of course, that for more details, we hope that you will read the paper and the special issues that we wrote.